Welcome to another episode of Code for Thought Byte-sized. In this final episode of Byte-sized before the end of 2022, I'll be talking about testing, specifically testing your Python code. This is the accompanying episode to the in-person and interactive Byte-sized RSE session from the 13th of December 2022. In the first part, I want to give you a flavor of testing your Python software, and then I will be talking to Peter Hill, a Fellow of the Engineering and Physical Sciences Research Council in the UK, or EPSRC, how he is using tests in his Python code. Testing is a vital part of software engineering. After all, you want to make sure that what you produce actually works. However, testing approaches and methods have changed quite a bit over time. When I started developing software, testing was something you did after you wrote your code. Or it was very ad hoc, like running your code in a debugger or using print statements to check values while the program is running. In fact, in those days, common development processes, often called waterfall processes, put the bulk of the testing after the software was developed. There are a number of problems with this. First, relying on ad hoc testing alone is a little bit like playing Russian roulette with your software quality. And leaving testing until you've finished with your code makes finding bugs all the harder and more time-consuming, even more so for large software packages developed by teams of engineers. Which is why modern software engineering takes a more systematic approach to testing by integrating and automating tests directly into the development process. And in fact, in test-driven development, for instance, testing is put, as the name suggests, right at the front of writing code. But before we start talking about how to build tests in Python, we should clarify what levels and what types of tests are commonly used. You probably heard of unit tests, where a unit is a small piece of code, typically, but not exclusively, a function or class method we want to test. The unit test itself is typically a standalone method and will be part of a group of other tests, grouped together in test cases and test suites. Unit tests are what I will discuss in more detail a bit later. The next level up are integration tests, which is particularly important for more complex software applications and packages. Integration tests check the correct operations of software modules and packages rather than individual components. And finally, we have system tests, which check the end-to-end operation of the entire software and everything needed to run it. In your development, you will probably write loads of tests, unit tests specifically. And Python, like most other programming and scripting languages, come with powerful tools to help build them. So for instance, PyUnit is a testing framework that comes built straight into Python, and you usually call it by importing it via the Unittest module. A very popular alternative is a framework called PyTest, and in my conversation with Peter Hill, he will tell us a little bit more about it later. Like PyUnit, it has been around for a long time. And there are of course other further test packages you may want to use, but these two are probably a very good starting point. You should be aware that although they are similar in what they do, there are differences in which they are being implemented, so take a look at the documentation. The episode notes provide links to both of these packages. Integrated development environments and editors like PyCharm, Visual Studio Code, or Emacs provide features or plugins that let you run your test suites while developing. Writing tests while developing your code is a very powerful way of making your software more robust, but it does take discipline. In return, it will change the way you think about and develop code. When you write a function, method or class, think about how you would test it. This often leads to writing leaner code, which in addition to making the code more robust, also renders it more manageable. And this principle holds even for writing tests for existing or legacy software that has little or no testing. In this case, the only way to add unit tests often is to rewrite sections of the code, or refactoring, as we call it. As mentioned before, Python has a lot of support for writing and running tests, so creating them should be straightforward. Convention has it that names for test methods start with test underscore. If a test is associated with a specific method or function, it's useful to call it test underscore followed by the name of that function. At the heart of the test method is the assert statement, which verifies that an expected value matches the returned value of an operation or method. But assert statements not only allow you to check expected values, they can and should be used to check edge cases and evaluate error handling. Python test frameworks provide a plethora of different methods and tools to build your test code. There are two that I would like to highlight in particular, and these are called fixtures and mocking objects. A fixture is used for setting values, providing features before you run your tests. Fixtures can be reset at different levels. They can be run once for the entire test suite or run before every single unit test separately. Some fixtures provide setup and teardown methods that can be run before and after the unit test or test suite. Teardown, for instance, is very useful if you want to clean up your code or memory afterwards. Like using fixtures, mocking objects is another important tool. Mocking is used when your code or test code depend on external objects or functions. You can replace that dependency and the need to implement it with mock objects or functions. Say, for example, your code writes to or reads from a file and you use an external file writer for it. Rather than implementing and using this file writer, you can create a mock file writer object that provides you with the same interfaces, but without the complexity of using it in your test. Fixtures and mocks are common practices in modern-day testing. Once you've written your test, the question is when and how to run them. A major advantage of unit testing and using Unittest frameworks is that you can run and should automate them. And that way you never forget to run them. Git, for instance, provides you with so-called pre-commit hooks that allow you to run your tests before committing them to your repository. And GitHub Actions allow you to run tests when checking in or merging code. Other platforms such as Bitbucket, etc. offer something similar. In addition to unit test frameworks, there are also other tools you should consider for your testing process. Here's a short and not a particularly exhaustive selection. Coverage.pi is a tool that measures the amount and percentage of your code covered by your unit tests. It also highlights which sections are not covered by unit tests, which may be very useful for you to identify which part needs more work. There are also tools to help you enforce coding styles and spot errors in code, for example, mismatched return values. Examples for that are, for instance, Flake8, Pylint, and Black. Again, you will find the links to all of these packages in the episode notes. Like your unit test code, unit tests and tools can be integrated into your automated build and deployment processes. And I can't begin to tell you how many times these tests have saved my colleagues and myself from introducing bugs, so do make use of them. So let's say you've written a lot of unit tests and have a high test code coverage. All tests are passing at 100%. Great job, well done, but there is a fly in the ointment. 100% pass rate is no guarantee that your code is bug-free. Firstly, your test code itself can contain errors. And secondly, you may have code that you haven't tested yet. But also, the results your software produces may not make sense or meet expectations from a research or scientific point of view. Basically what this means is the unit tests may show your software works, but the assumptions you put into the software may have been wrong. In short, your unit and integration tests, vital as they are, may not be enough. You may have to run additional checks that the output your software produces falls into an expected range, or meets certain edge cases. This indeed can become quite tricky when the software is based on, for instance, Monte Carlo simulations, or modeling, where often a large number of runs with different input parameters are being used. Think, for instance, of epidemiological modeling software. Having said all that, unit tests and unit test suites provide the baseline for your software. Tests and automated testing are vital when you work in teams and on large software packages. And if you share your code or make it publicly available, it is a great way of building confidence in users of your software. And now enough said, and on to my conversation with Peter Hill. Hello, Peter. Thanks very much for coming today, and nice to see you again. But before we start, let's do a quick introduction. You've been on the show before, but I think it's been quite a while ago.
Indeed, yeah. Thank you for having me. I'm Peter Hill. I'm a EPSRC Research Software Engineering Fellow. I work in plasma science, and my work is basically about trying to improve the software sustainability of the plasma software ecosystem.
And software sustainability is kind of the theme today because we want to talk about testing, in particular Python testing. So let's go straight into it. And I'm interested to see how you approach testing.
So I heavily rely on PyTest, I would say, is my main tool of choice for doing it. But I often come in on legacy systems, legacy codes, right? And a good definition of that is software that doesn't already have tests. And so there's slightly different approaches that you need to take with legacy software versus sort of greenfield software when you're thinking about tests. And also because obviously I work with scientific software, the particular approaches you take with scientific software, trying to test that compared to testing more corporate software. I think the easiest thing to think about in terms of starting off testing any kind of scientific software is sort of capture the current state of it in something like a golden answer test.
Right. So is that the outcome of what you expect as a scientific result then?
Indeed, yeah. So you have the domain expert or something run the code in some fairly typical configuration that they're like fairly confident about the results. They say, yeah, that looks right to me. As the RSE that's actually trying to implement the tests, you say, okay, great. I'll take your input and I'll take your output, maybe just a slice of your output, and I'll say, that's the test. And you code that up so that you can automate it. And once you've got that in place, then you can start doing the more perhaps typical testing that you might think about, which often requires some refactoring to get to more sort of usual unit tests.
I think that's quite an interesting subject, in fact, to how to deal with legacy code, which has little or no testing very
Yeah.
often. I mean, I've encountered that too in the commercial world too, one might add. But what about greenfield testing? Let's say that you would start from scratch. So what would your testing approach be there then?
A lot of people advocate test-driven development, where you write the
Right.
tests first, and then you go, okay, that's my sort of specification for the software.
Mm.
But I find in practice, I can't actually write code like that.
Why is that, do you think?
It's just perhaps a matter of discipline, but
Mm.
also in some way, scientific software, and perhaps a bit true for business software as well, it can be difficult to know exactly what this thing should do first, that you might need some exploratory writing some code to help you think about what the problem actually is. So even if you don't write the tests first, they need to come very soon after. You're continuously testing as you go along, even if you're not writing for scientists, perhaps. They're continuously testing as they go along, even if they're not writing like a testing suite, testing framework. So I think it's just important that you codify that as early as possible, that you actually do write a test
Mhm.
suite that you can run automatically. I tried to write that as unit tests. You write one function, then you write the tests that go with that function. And then you can start thinking about what are the edge cases. And I find when I write the tests, that's when I can start thinking about, okay, what happens if I put a 0 in? What happens if the list is empty? What happens if I get negative numbers when I'm only expecting positive numbers? That thinking about what are the edge cases? When can this fail? What do I actually expect this function to produce? I find my thinking a bit clearer when I'm writing tests.
You mentioned PyTest. So what does PyTest bring to the table? You rely heavily on it, you mentioned.
Yeah, because Python has a built-in unit testing framework,
Mhm.
the Unittest module,
Indeed.
and it's fine, it works well, but it just requires a bit more boilerplate and a bit more structure imposed on the way that you write your tests than PyTest does.
Mhm.
PyTest, you write a file called test something.py. In it, you write functions called test something, and the functions have just plain assert statements in. And PyTest finds those files, runs all those functions, captures any failed asserts. You don't need to write classes that derive from particular instances. You don't need to call particular methods assert almost equal. You can just write assert. I find that just much easier to use. And there's lots of plugins for it. So there's like coverage plugins, which also help you guide, especially for legacy software, guide where you should be writing tests. And so I just find that very easy to use.
So there are a couple of questions with regards to PyTest or testing in general, but let's talk about PyTest. For instance, in some test cases, you might want to start from a specified and a defined state. So like setting variables, etc. How would you do that with PyTest?
So this is the idea of fixtures, where you have some setup code, perhaps, that runs before several tests. So the way that I write it is I write my test and I write another version of the test and I copy and paste all that setup. And after I've done that a couple of times, I go, okay, that gets called out. It goes into its own function. You annotate that with a PyTest.fixture decorator. So like at PyTest.fixture, just on that function. And then you pass the name of that function as an argument into your test function. And PyTest takes care of calling that function and passing it in. And that way you can have some setup that is common and you have a lot of control over that function. So for instance, if it's an expensive setup, maybe you need to calculate something expensive that takes a couple of seconds, or you need to copy some files or write some files. You can put that in a fixture and tell PyTest to only run it once for the entire test suite. And so it can pass in the same object each time. That can save you a lot of time.
So we talked about fixtures, so when you need to have certain starting points. But likewise, some tests may also require a little bit more technology stack behind it. Like you need to have some kind of network without really the network, if you know what I mean. So but you need to pretend that there is a technology stack, but there's some functionality behind. So how would you do that?
Again, I think this is something that's built into the Python's included Unittest module, but PyTest has an easier version of it, which is mocking, as it is called in other languages. But Python's really, really nice for this, because monkey patching, you can just take some module and just change its properties how you like. And so this makes it really easy in Python to take something like a network call and just sub out its implementation of doing the network call for your own function, which can just return perhaps some hard-coded JSON. PyTest, again, makes this very easy. There's a monkey patch fixture that you can pass in, and then you can use it like a context manager. So you can do like with monkey patch, change some things, and then outside of the context, it changes them back. So that can be very, very useful for instance, if you've got some Python module which can be run as a command line script, you might want to test that you can call that correctly. And so you could use like a sub-process, and there's some overhead to that. So you can just monkey patch sys.argv as if you were passing in command line options and then call that function. Just another example of the sort of power of monkey patching.
So what kind of code static analysis tools?
Yeah, so I use Flake8. Have also used Pylint. I think I got too frustrated at Pylint at some point and switched over to Flake8. So Flake8 is a very powerful tool. That's partly because it has a huge list of warnings and errors that can capture things like variables being used before you've actually assigned to them, capturing typos, and the opposite, the other way around, of variables that get assigned to and never get used. And so they're just mistakes that are very easy to make. And then there are more sophisticated tools like MyPy, which does static type checking. In Python, you can optionally annotate variables and functions with their types. It doesn't affect anything at runtime, but you can do static analysis to check if a function returns a string that you're not trying to then use it like an int. Those are probably the two main tools that I use for static analysis in Python.
Let's talk a little bit about automation. So what can you do there?
So automated tests are essential because exactly right, you can forget to run the tests. I have worked on projects previously that had good test suites and people would just occasionally forget to run them and push broken code. You can automate tests locally, for instance, through Git pre-commit hooks. I personally don't tend to do that because that requires some more effort. And I just have everything set up in continuous integration, right? So that's something like GitHub Actions or Bitbucket pipelines or GitLab, whatever they call their things, pipelines perhaps too. And so that means that it's not possible for anybody in the project to forget to run the tests. And once you've got that that's set up, that means you can gate commits. And you can also hang loads of other stuff off that. So you can hang the flake8, the static analysis stuff. You can also automate that on the CI. Again, I mentioned Black, the formatter, so you can automate that. The last thing I try to automate is the publishing as well, because that can be a faff. If you're publishing a Python package, you probably want to check that it runs in different versions of Python. And so there are tools like Tox, which can use multiple different versions of Python and run your test suite. I don't tend to use that. I just tend to use like GitHub Actions and tell it to use different versions of Python.
Well, thank you very much, Peter. That was great. And all the best.
Thank you.
Cheers.
Bye.
Thank you for listening to this episode of Code for Thought Byte-sized. The content and the interactive Byte-sized RSE sessions are created and run by Jeremy Cohen from Imperial College London and Steve Kraut from Southampton University. The podcast episodes are produced by Peter Schmidt. Finally, we'd like to thank UNIVERSE-HPC for their continuous support. And with that, goodbye.